Hi, and welcome to Matlab 316. This is a lecture of continuing of section 2.3, the secant method and the method of false position. So these are the final root finding algorithms that we're going to take a look at. So let's just note that the major drawback to Newton's method, which we saw was a quadratically converging root finding method, is that you need the derivative, and that might not be easy to compute. So what the secant method does is it allows us to modify Newton's method so that we don't need the derivative. So basically, we're going to use the secant line approximation to the tangent line. So let's just recall Newton's method. Newton's method is this. The nth estimate of the root we find from the n plus first estimate, and we subtract from that the function evaluated at that n plus first estimate of the root, and then the derivative also here. Okay, that is we have our n plus first estimate of the root, and what we're doing is we want to find with Newton's method, we're using the tangent line here, but in this case, what we're going to do instead is we're going to pick another value over here. Let me just call it x, and then this value here will be f of x, and then this value here would be f of Pn minus 1, and we are then going to use that secant line between those 2 points as an estimate of the tangent line. So that goes through the 2 points there, and it's an estimate of the tangent line. And the slope of that tangent line is of that secant line is the delta y over delta x. All right. So we have if we looked at the definition of the derivative, this is the definition of the derivative, and we're going to evaluate it at Pn minus 1. That is the limit as x approaches Pn minus 1 of f of x minus f of Pn minus 1 divided by x minus Pn minus 1. That's the definition of the derivative. So now we're going to suppose we have 2 close points, and in fact we kind of want to use points for which we've already evaluated the function. So we in fact know that f of Pn minus 2 is likely to be close to f of Pn minus 1, particularly as we're getting close to the root. So then what we're going to do here was we're going to want to get rid of this guy out of Newton's method. So we're going to say that f prime of Pn minus 1 is going to be f of Pn minus 2. We have already evaluated that from the previous iteration. We're already evaluating that number, f of Pn minus 1, during this, and then we have to do this one additional calculation here, subtract those 2 numbers. And then we're going to take that and we're going to plug that in for the derivative. So this guy here is going to be put in here. That is going to be substitute that in for the derivative into the Newton iteration formula. I'm going to go ahead and do that, and I will have the method of the secant method. That will be, the calculation will be done in the following manner. The nth iteration for the root will be the n plus first one minus f of Pn minus 1 times Pn minus 1 minus Pn minus 2 divided by f of Pn minus 1 minus f of Pn minus 2. Okay, be careful not to confuse the indices. Okay, notice that this is n minus 2, and then this one is n minus 1. So that is the secant method. Okay, it's a modification of Newton's method where we're instead of using the tangent line, we're using the secant line to project down onto the x-axis and find the next estimate for the zero of the function. So because we have that, let's just maybe scroll back up, because we have this situation where we have Pn minus 2 and Pn minus 1, we actually need two initial values in order to start the secant method, P0 and P1. So we would pick those. In this illustration here, we have chosen P1 right here and P0 right there and P1 right here. And then you can see the secant line. That is that line right there. That secant line crosses the x-axis right there. And then that becomes the next estimate for our root. And then you keep finding those secant lines. Okay, just maybe a memory aid, a language lesson. The word secans is Latin. It's a verb. It means to cut. Okay, and so it's as opposed to the also Latin word tangens, which means to touch. So in the tangent line is touching the curve at one point, and the secant line is is a cut in the sense that it doesn't actually, this function is convex up, so it doesn't cut it, but it's a straight line connecting the 2 points. And this one we see easily, we can see words that come from this that have the word cut in. So there's bisect, right? There's that cut into intersect, like that, or resect. Okay, resect is what happens to you when the surgeon cuts something out. Okay, so let's compare this method with Newton's method. And imagine us trying to find the log of 5. Okay, this maybe doesn't immediately look like a root finding problem. So then you have to think to yourself, okay, I'm wanting to find the log of 5. That is, x is equal to the log of 5. That would mean that e to the x would be equal to 5, and that means that e to the x minus 5 would be equal to 0. So if I'm trying to find the log of 5, I want to find the 0 of this function. So here's a MATLAB produced graph showing for this function the Newton method versus the secant method. Okay, so we've got the Newton method performing better, and you can see that waterfall situation there. We've got the secant method. Okay, it's better than bisection, but not as good as not as good as Newton. The secant is in the middle, so it's a little bit slower than on Newton's method. Okay, you can see the error by an iteration number there. And so this is this first one here is the same function. This is for the Newton method here. We are taking an initial value P0 equal to 5, and on the secant method, I took a P0 equal to 5 and a P1 equal to 4. And then you can see a different performance here, but you can still see that the Newton method is faster than the secant method. This was where we start with the root. We start with our initial guess rather far away from the root. And this with P1 is 29. Okay, so secant is slower than the Newton method. All right. I just said that right there. And we're not going to go through the proof here, but you can show that the secant method has an order of convergence of 1 plus root 5 over 2, and that is approximately 1.6. So that alerts you again that that's that order of convergence. So we had the order of convergence is 1 for the bisection method. Order of convergence is 1.6 roughly for the secant method. And then the order of convergence for Newton's method was 2. This is Newton. Okay, you see the waterfall in both the secant and the Newton method. And so we've been talking about this a little bit in class. There's been a lot of good questions about which method should you use and which initial guess should you have. And so both of these methods are usually used after you get to a smaller interval. So you start with another algorithm, typically the bisection, and then you move to one of these two methods, depending on whether you want to compute a derivative or not. Just out of interest, this is this number is actually kind of a special number. It showed up here, which is kind of interesting. And that number is actually often denoted by, and it is the golden ratio. And it is this number here, 1 plus root 5 over 2. And it is that number where if you were to consider a rectangle like this, and you were asked, where should I draw the line in the rectangle so that the aspect ratio of this bigger rectangle will be the same as the aspect ratio of this rectangle? So where along there should that be? And then you would do that same division here, make that ratio, that rectangle there have a similar aspect ratio, and then you could do it again here and again here. You get this kind of that very pleasing pattern, and this golden ratio actually shows up quite frequently in architecture or in art. It has a pleasing look to it. It also shows up in the Fibonacci sequence. There's Fibonacci sequence like that. And if you look at the ratio of adjacent Fibonacci numbers, so for example, 1 over 1, that's 1. And then you look at the ratio of the next two Fibonacci numbers, that would be 2 over 1 is 2. And then the ratio of the next two, 3 over 2 is 1.5. And then 5 over 3 is 1.66 repeating. 8 over 5 is 1.6, and then 13 over 8. So I'm just like this, 13 over 8, and I'm going to go 21 over 30, 21 over 13, and then I would go 34 over 21 and 55 over 34, and I'm just going to write down those numbers. 13 over 8, I got 1.625. 21 over 13, 1.615, and there's some more numbers there. 34 over 35, let me say 34 over 21, 1.619. 55 over 34, 1.617. And you can see this appears to be converging, and indeed it is converging. In the limit, the ratio of the limit as n goes to infinity of Fibonacci number n plus 1 over Fibonacci number n is equal to 1 plus root 5 over 2. There you go. Something about that special number. So secant method is straightforward in the sense it is straightforward. It is just Newton's method using the secant approximation for the derivative. Okay, so let's talk about one last method. Newton's method and the secant method may diverge. And that depends on what the derivative looks like near the root. The bisection method always converges, given that we can find a function value on either side of opposite signs, and that the function is continuous. And so let's ask clearly, why does the bisection method converge slowly? Okay, so the method brackets the root. What do I mean by that? We have some sort of continuous function. It has a root, and we must start on the bisection method. We must find a value, and we must find another value such that f of a times f of b, the sign of that is -1. They have to be of opposite sign. Okay, so the method brackets the root, and after n steps, the root lies between an and bn. So we get that, and that interval just keeps getting smaller. And the slow convergence is a result of always picking the middle. Okay, so let's look here what we would do. We would go a plus b. We'd be somewhere right here. We would pick the middle. So this would be a1. And then this guy we would recognize that this is negative. So then we would go in this interval here. And then we're actually, we were noticeably closer. But when we go to this next one, we're going to be right here. We're going to go halfway, which is going to be here. And then we're going to go halfway like that. But we're never going to, even if we were to come, even if halfway had been right here, we're still going to move away halfway over here. So sometimes we're actually further away on further iterations because we're always going in the middle. We're not looking at what the function looks like in between in the interval. We're not using that at all. We're just always going into the middle, no matter what the function is. Okay, so one way of increasing where you choose that point, rather than using the rather than bisecting the interval, you can use the secant approximation between A and B. And that's what we call the method of false position. Okay. So, I mean, there's other options than bisecting. I think in class we talked about we could trisect or something like that, and then you'd have a few more function evaluations. That's another option. So there's other options, but let's look at this method of false position. So we're gonna start with two numbers, P0 and P1, and we're gonna have the situation like bisection. We're going to have that f of P0 times f of P1 is less than 0. And then so we have that P0 and P1 bracket the root. The one is on one side and one is on the other. Okay. Now in bisection, for bisection, we pick P2 to be midway between P0 and P1, like that. Okay. For false position, we try to be smarter. We pick P2. How do we pick P2? We don't pick it in the middle. We pick it to be the x-intercept of the line joining the 2 points here. Let me write that out. We pick P2 to be the x-intercept of the line joining P1, f of P1, and P0, f of P0. Okay, that looks like this then. P2, our next estimate of the root, is going to be P1 minus f at P1 times P1 minus P0 divided by f at P1 minus f at P0. Okay, what does that look like? Here, I think once you see a picture, it'll be fairly obvious. We imagine that we have a function. There it is, right there. We're trying to find the root. The root is right here. Okay, so we pick P0. You know, we're going to have P0, say, right here, P0. And then we're going to have P1. Let's say P1 is over here. Okay, then we have here f of P0. And here we have f of P1. Okay, so the bisection method would just be to bring P2 in here, right in the middle. And that's not using any information about the function. The secant, the method of false position is to use the secant line between those 2 points. So I'm just going to draw a line between those 2 points. So this is the line that goes like this, like that. And then use this position, the x-intercept of that, use that for P2. Okay, so it's using some information about the function to decide where to go in the interval. And this is a better method. Okay, so then just like the bisection method, once we've identified this P2, we would then move to working in this interval here, because that interval there brackets the root. Okay. Like bisection, the method of false position is guaranteed to converge, and it does so with linear order. You don't get any quadratic convergence, but it is a little bit faster than bisection because you are not going in the middle. You're cutting the interval a little bit more clever. So that's it's typically slightly slower than the secant method, and we're paying that price for guaranteed convergence. So this is sort of nice. We've combined a couple of different ideas, bisection with the secant method, to get a more sophisticated method having the benefit of both. So what we're going to do right here is just get a summary of the methods that we have seen. Summary. Okay, let's list the methods that we've seen for finding roots. Okay. Bisection. We saw a bisection method. We saw Newton's method. Then we saw the secant method. And finally, we saw the method of false position. Okay, for each one of these methods, we talked about the order of convergence. We have a number of starting points. We have the number of function evaluations. This is per iteration. We have the accuracy, and we have the efficiency. Okay, this is basically how quickly we can accuracy, efficiency, how quickly we can get to a good answer, and we have the robustness. That's like whether we're going to get there for sure or not, or we're going to have, are we going to respond overly dramatically to small changes? Okay, so the order of convergence, we saw that the order of convergence of the bisection method is 1. It's linear convergence. We saw that the order of convergence for the Newton method is 2. It is quadratically converging. We just saw here in this lecture that the order of convergence for the secant method is 1 plus root 5 over 2, and that's approximately 1.6. And that the false position method is also a linearly converging method. Okay, for the bisection, we need 2 points to start. For Newton's method, we need 1 point to start. For the secant method, we need 2, and for false position, we need 2. How many function evaluations do we have to do? Bisection 1, Newton 2, secant, and false position 1. The bisection is sort of moderate in the how quickly can we get to the root. Newton is high, secant is high, and the false position is more moderate. Okay, that's really a reflection of what's in this column here. The bisection is highly robust, as is the false position method. You're going to get there. These ones this one is moderate. You can have some problems if the derivative is not bounded away from 0 near the root. And this one here is moderate to high. It's a bit better in the robustness because you're not taking derivatives. You're less you have less worry about if you've got a problem with the derivative. Okay, I'll just kind of say a couple of more things here. That would be, I recommend for you to ask that question we've always been asking, what does Matlab do? And so there is a command here, Fzero, and you give it a function, you give it a starting point or interval, and there's some options that you can pass to it here. What I'm of course going to suggest you do is on MATLAB, you go help Fzero and read the documentation. This updates when MATLAB improves their thing or makes it more sophisticated, and also it usually gives you a good idea of sort of a industry proven method of doing this. Okay, so what does this function do? I mean, it finds the root of the function near x0. You have to provide the initial where to start, and x0 can be a point or an interval. And the options are some things about like there's a set of options you can pass, the tolerance that you want, the max number of iterations. That's there's to take a look. So there's take a look at how MATLAB does that. Okay. All right. Final thing we're going to say here. Computing roots of polynomials. So we're going to consider polynomials of degree n, and we're having for this discussion here, the coefficients are going to be real. So we've got a polynomial of degree n. And so the fundamental theorem of algebra tells us that P of x has n zeros if we include multiplicity and we allow for complex roots. The good news here is that root finding for polynomials is easier than for general functions. So let's just talk about a couple of things. Our textbook, Burden-Ferris, let me just call that BF, Burden-Ferris, our textbook describes, I'm not going to test this, but I want you to be aware of it, describes Horner's method. Horner's method. And that is essentially Newton's method. With efficient polynomial evaluation. And what is efficient polynomial evaluation? You ask yourself, what is that? That's using the nested form. We've seen this before. Okay, so you do the minimum number of computations to evaluate the to evaluate the polynomial. That's the Horner method. And then we've got a standard. This is a standard approach. This is what MATLAB does for its command roots. So this is MATLAB roots command. So what it does is it forms a companion matrix. Let's write out what that is. So the idea is to form a companion matrix. And that matrix is going to look like that. Let's put the polynomial for which we want to find a root so we can see how this looks. So the polynomial looks like this: xn plus an minus 1, xn minus 1 plus an minus 2, xn minus 2 plus ... plus a1x plus a naught. Okay, so the first thing to do, the first thing that is done is this guy here. It makes it a matrix like this. This is, of course, it's going to depend upon the degree of the polynomial. The matrix is a sparse matrix. It looks like this. So this is so in the last column here, we're getting the negative of the coefficients in order from A naught up to AN, and then we're getting a series of ones along here. So we got, this is going to keep going like this, and the last one, that'll be a 1, and then minus AN minus 1. So there's the diagonal of ones coming down here like that. Okay, that is what's called the companion matrix associated with this polynomial. And it is the case that the roots, you're going to love this, the roots of P of X, the zeros that we want to find, are the eigenvalues of A. So that's what the MATLAB roots command does. The problem is simplified when we're doing a polynomial root find. Now you'll notice here we're not using any of the methods this is not using any of the methods we talked about, not using bisection or anything. It's a completely different approach. Okay, so there's a MATLAB demo that you could run from that MATLAB code on our Canvas page, and this is this program that you should run and take a look at what happens. This computes the roots of a polynomial of degree n, where the coefficients are normally distributed. So they're taken from this standard normal distribution. And here, if we make n larger, as n increases, the roots cluster on the unit circle. So that's kind of an interesting thing to see. So run that code, and you can change the value of n, and you will see that as n gets larger, the roots tend to cluster on the unit circle. Okay, so that is our last two methods of root finding. We have the secant method, and then using the idea of the secant line, we adjust the bisection method, and we get the method of false position. Thanks, guys. Bye.